The information provided in this video is for educational and entertainment purposes only. Operating heavy machinery or commercial vehicles involves significant physical risk and requires specialized training, professional certification, and adherence to federal and state regulations, including those set by the Department of Transportation and the Federal Motor Carrier Safety Administration. This content does not constitute professional training, legal advice, or career counseling. Always consult with certified instructors and regulatory bodies before attempting to operate any vehicle discussed. Viewers are advised to conduct their own due diligence regarding licensing requirements and safety protocols. The American economy is exactly 3 days away from total collapse at any given moment. That is not a hyperbolic statement or a conspiracy theory. It is a logistical reality. If every heavy vehicle in the United States stopped moving right now, hospitals would run out of critical supplies within 24 hours. By the second day, gas stations would run dry, and communication networks would begin to fail as backup generators lost their fuel sources. By the third day, the food supply in every major metropolitan area would be depleted. We live in a civilization that is physically built and sustained by massive, roaring engines and tens of thousands of pounds of steel. Yet, most people driving alongside these giants on the I-95 or the I-10 have no idea what they are looking at. They see a truck, but they do not see the difference between a Class 7 and a Class 8 vehicle. Nor do they understand the specific engineering required to move a 100,000-pound transformer across a mountain pass. This is not just a video about big machines. This is a masterclass in the mechanical backbone of the United States. Today, we are breaking down the complex hierarchy of heavy vehicles, the rigorous physics that keeps them on the road, and the specific roles each one plays in keeping the modern world from grinding to a halt. By the end of this deep dive, you will understand the American landscape through an entirely different lens, recognizing the specialized tools that build our cities and stock our shelves. To understand heavy vehicles, we must first understand how the United States government classifies them. This is not arbitrary. It is based on the Gross Vehicle Weight Rating, or GVWR. The GVWR is the maximum operating weight of a vehicle as specified by the manufacturer, including the vehicle's chassis, body, engine, fluids, fuel, accessories, driver, passengers, and cargo. The Department of Transportation divides vehicles into 8 distinct classes. For the purpose of this deep dive, we are focusing on the heavy-duty end of that spectrum, specifically classes 7 and 8, though we will touch upon Class 6 to show where the transition into true heavy-duty territory begins. Class 7 vehicles are those with a GVWR between 26,001 and 33,000 pounds. These are the workhorses of the urban environment. Think of the large box trucks used by major furniture retailers, or the city buses that navigate tight metropolitan corners. These vehicles typically have 2 axles, but their weight capacity puts them in a category that requires a commercial driver's license in most jurisdictions. The engineering challenge here is balance. A Class 7 vehicle must be powerful enough to carry a massive payload, but nimble enough to operate on city streets that were often designed long before such vehicles existed. Historical trends show a shift toward more aerodynamic designs in this class to combat rising fuel costs, even for short-haul urban routes. However, the undisputed king of the American highway is the Class 8 vehicle. Anything with the GVWR over 33,000 pounds falls into this category. This includes the classic 18-wheeler or semi-truck, but it also includes massive dump trucks, refuse haulers, and specialized heavy-haul rigs that can reach GVWRs of well over 80,000 pounds with special permits. When you see a tractor-trailer hauling a massive piece of construction equipment or a line of 3 trailers being pulled by a single tractor in states like Nevada or Utah, you are witnessing the absolute limit of automotive engineering on public roads. Let us look closer at the anatomy of a Class 8 tractor. The tractor is the front part of the rig, containing the engine, the cab, and the fifth wheel. The fifth wheel is not actually a wheel. It is a heavy-duty coupling device shaped like a horseshoe, designed to provide the link between a semi-trailer and the towing truck. This connection point is a marvel of physics. It must allow for the articulation of the trailer, meaning the trailer can swing left and right, while supporting tens of thousands of pounds of downward force. This is where the concept of the bridge formula comes into play. Federal law limits the weight of vehicles on the interstate highway system to protect the structural integrity of bridges. The formula calculates the allowable weight based on the number of axles and the distance between them. This is why you will see some heavy-haul trailers with dozens of wheels spread out over a long distance. They are literally spreading the weight so they do not crush the pavement or collapse a bridge. The engines powering these behemoths are vastly different from what you find in a consumer pickup truck. A typical Class 8 engine like a Cummins X15 or a Detroit DD15 is a straight-six turbocharged diesel engine with a displacement of around 15 liters. For comparison, a large SUV might have a 5 or 6 liter engine. These diesel engines are not built for speed. They are built for torque and longevity. Torque is the rotational force that allows a truck to move a massive load from a dead stop. A high-end semi-truck engine can produce upwards of 2,050 pound-feet of torque. These engines are designed to run for over 1 million miles before needing a major overhaul, reflecting a historical trend of reliability that allows logistics companies to plan their operations years in advance. Beyond the standard freight hauling semi, we have the world of vocational heavy vehicles. These are machines designed for a specific task rather than general transport. Consider the concrete mixer. This is one of the most mechanically complex heavy vehicles on the road. It isn't just carrying a load, it is a mobile chemical processing plant. The drum must rotate at a specific speed to prevent the concrete from segregating or setting prematurely. The weight distribution is a nightmare for engineers because the center of gravity is high and constantly shifting as the wet concrete sloshes around. Operating one of these requires an understanding of fluid dynamics as much as driving skill. Then there are the heavy dump trucks, often seen in Class 7 and 8 configurations. These are built with reinforced frames to handle the shock of several tons of rock or dirt being dropped into the bed from a height. The hydraulic systems required to lift a fully loaded bed are capable of exerting thousands of pounds of pressure. Case studies in construction safety often highlight the dangers of these vehicles when operating on uneven ground. If the truck is tilted even slightly when the bed is raised, the center of gravity moves outside the wheelbase, leading to a catastrophic tip-over. In the realm of infrastructure, we cannot overlook the heavy vehicles used in road construction, such as pavers and cold planers. A cold planer is a massive machine that grinds up old asphalt, recycling it into a conveyor belt that dumps it into a waiting truck. These vehicles move at a snail's pace but possess incredible power. They are the front line of American infrastructure maintenance. Similarly, the crane truck provides the literal lifting power for our skylines. These vehicles must balance their own weight with outriggers, large metal legs that extend from the side of the truck to provide a stable base, so the crane can lift loads that would otherwise flip the vehicle. We also have to discuss the evolution of the refuse truck. The modern garbage truck is a heavy-duty hydraulic press on wheels. In many American suburbs, you will see front loaders or side loaders that use automated arms to grab bins. These vehicles operate in high-stress environments, with constant stop-and-go movements that put immense strain on the braking systems and transmissions. Historically, these were some of the loudest and most polluting vehicles on the road, but recent trends show a massive push toward compressed natural gas and even electric powertrains in this sector to reduce the impact on residential neighborhoods. The sheer diversity of heavy vehicles in the USA reflects the diversity of the American economy itself, from the logging trucks of the Pacific Northwest, equipped with specialized cages to protect the driver from shifting timber, to the massive fuel tankers that replenish our airports. Every vehicle is a specialized tool. The logistics of operating these vehicles involve a complex web of regulations, including hours of service, HOS, rules that dictate how long a driver can be behind the wheel, ensuring that the human element is as reliable as the mechanical one. We are going to dive much deeper into the specific mechanics of these systems, the economic impact of heavy hauling, and the future of autonomous heavy vehicles in the coming sections. This is just the beginning of our deep dive into the machines that move America. To grasp the true scale of the heavy vehicle industry in 2026, we have to look past the standard delivery truck and into the world of specialized heavy hauling. Imagine a logistics manager named David based in a hub like Columbus, Ohio. In 2026, David is not just managing drivers. He is coordinating a high-stakes mechanical ballet. He is currently overseeing the transport of a 180,000-pound power transformer destined for a substation in the Appalachian Mountains. This is where the standard Class 8 truck reaches its limits and the world of superloads begins. A superload is any load that exceeds the standard weight or dimension limits set by the state, often requiring a multi-axle configuration that looks more like a train than a truck. For a load of this magnitude, David cannot use a standard flatbed trailer. He employs a modular trailer, often referred to as a Goldhofer or a multi-axle platform. These trailers can have upwards of 12 or 18 axles, each capable of independent steering to navigate tight mountain switchbacks. The step-by-step process of preparing this vehicle is a feat of engineering. First, the weight must be distributed so that no single axle exceeds the pounds per linear inch limit of the road surface. If the weight is too concentrated, the tires will literally sink into the asphalt, causing thousands of dollars in infrastructure damage. Historical trends in heavy hauling show that the permit process for these moves can take months, involving bridge engineers who calculate the exact stress the vehicle will place on every overpass along the route. The tractor unit pulling this load is often a specialized heavy haul truck with a high-torque engine and a planetary gear set. Unlike a standard semi, these trucks often have a heavy-duty cooling package mounted behind the cab because the engine is working at maximum capacity for hours, generating enough heat to melt standard components. David's team must also coordinate with pilot cars. In 2026, these are not just trucks with yellow lights. They are mobile data centers equipped with height poles and real-time sensor arrays to ensure the load clears every power line and bridge. A single miscalculation on a 15-foot high load can result in a catastrophic infrastructure failure, which is why these operations move at a walking pace in certain sections. Now, shift your focus from construction to the hidden giants of the energy sector. We often take for granted the massive fuel tankers that traverse our highways. A standard Class 8 fuel tanker carries approximately 9,000 gallons of gasoline. In 2026, the logistics of these vehicles have become even more complex with the integration of multi-compartment tanks that carry different grades of fuel or even renewable biodiesel blends in a single trip. The physics of a liquid load is one of the most dangerous aspects of heavy vehicle operation. This is known as the slosh factor. When a tanker truck enters a curve, the liquid inside shifts to the outside of the turn. If the driver brakes or turns too sharply, the momentum of thousands of gallons of liquid hitting the side of the tank can create a centrifugal force that flips the entire rig. Case studies from the National Transportation Safety Board frequently cite liquid surge as a primary factor in tanker rollovers. To combat this, modern tanks are built with internal baffles, walls with holes in them that allow liquid to flow but prevent it from slamming from one side to the other. But what happens when these massive machines fail or crash? This brings us to the most powerful vehicles on the road that most people never hope to see in action: the heavy-duty recovery rotators. Imagine a 50-ton rotator like the Century 1150. These are not your neighborhood tow trucks. These are essentially mobile cranes built on a heavy-duty truck chassis. A rotator can extend its boom and rotate 360 degrees, allowing it to lift a fully loaded cement mixer out of a ravine without blocking all lanes of traffic. The cost of one of these machines in 2026 can exceed $1 million, reflecting the incredible engineering required to stabilize a vehicle that is lifting another vehicle of equal or greater weight. The outriggers on a rotator must be strategically placed on solid ground to prevent the recovery vehicle itself from tipping. This is a high-stakes scenario where the operator must understand load charts and center of gravity physics, as well as any structural engineer. We must also address the technological shift occurring in 2026 regarding the power plants of these heavy vehicles. While diesel remains the dominant force for long-haul trucking due to its energy density, we are seeing a significant rise in Class 8 electric vehicles for regional haulage. These trucks, such as the latest iterations of the Tesla Semi or the Freightliner e-Cascadia, utilize massive battery packs that serve as a structural part of the chassis. The potential outcomes of this transition include significantly lower maintenance costs, because electric motors have fewer moving parts than internal combustion engines. However, the trade-off is the weight. In 2026, federal regulations have been adjusted to allow electric heavy trucks a 2,000-pound weight allowance to account for the heavy battery packs, ensuring they can still carry a competitive amount of cargo. The braking systems on all these heavy vehicles are another area of deep mechanical interest. In a standard passenger car, you have a hydraulic system. In a heavy vehicle, you have air brakes. The fundamental difference is that air brakes are a fail-safe system. In a car, if you lose your brake fluid, you lose your brakes. In a heavy truck, the system uses air pressure to keep the brakes open. If the system loses pressure, massive springs automatically engage the brakes, bringing the vehicle to a stop. This is why you hear that distinct hiss of air when a truck parks. That is the air being released so the spring brakes can lock the wheels. Furthermore, heavy trucks use engine braking, often called a jake brake. This system modifies the engine's valve timing to turn the engine into a giant air compressor, creating significant drag that slows the vehicle without wearing out the friction brakes. This is critical for long mountain descents like the Grapevine in California, where traditional brakes would overheat and catch fire within minutes. Think about the impact on the American economy if these specialized braking and cooling systems were not maintained. Historical trends show that a single major mechanical failure on a heavy vehicle in a high-traffic corridor can cause a ripple effect that delays thousands of shipments, costing millions in lost productivity. In 2026, predictive maintenance sensors are now standard, using artificial intelligence to monitor the vibration of wheel bearings and the temperature of brake drums in real time. This data is fed back to managers like David, who can pull a truck for service before a component fails on the road. As we look at the sheer variety of these machines, from the rotators that save us to the tankers that fuel us, one thing becomes clear: the complexity of their operation is matched only by the necessity of their presence. But there is a specific category of heavy vehicle that most people see every day but never truly appreciate the sheer power and danger of. These are the vehicles that literally carve the path for all others. In the next part of this masterclass, we are going to tear down the mechanics of earth-moving giants, exploring how a single machine can move 30 tons of earth in a single bite, and the hidden hydraulic systems that make it possible. We will also look at the high-stakes world of heavy vehicle auctions, where these machines are bought and sold for more than the price of a luxury mansion. The scale of the machinery is about to get even larger as we move off the pavement and into the dirt. Off the asphalt of the interstates, we enter the realm of yellow iron. This is where the physics of heavy vehicles shifts from high-speed aerodynamics and rolling resistance to raw, low-speed hydraulic force. In 2026, the construction equipment market in the United States has reached an unprecedented level of technological sophistication. The machines are no longer just blunt instruments of destruction. They are precision tools guided by satellites and powered by high-pressure fluid dynamics. To understand the machines that reshape the American landscape, we have to start with the most versatile vehicle on any job site: the hydraulic excavator. Imagine a site foreman named Sarah overseeing a massive commercial development in the suburbs of Dallas. In 2026, her primary tool is not a clipboard, but a tablet linked to a fleet of Caterpillar 395 excavators. These are not the small backhoes you see in a residential alleyway. A Cat 395 weighs nearly 200,000 pounds and is designed to move mountains. The engineering at the heart of this machine is the hydraulic circuit. While a truck uses its engine to turn wheels, an excavator uses its engine to drive a massive variable displacement piston pump. This pump takes mechanical energy and converts it into hydraulic pressure, often exceeding 5,000 pounds per square inch. This pressure is then directed through a complex manifold of valves to the cylinders on the boom, the stick, and the bucket. The precision is what makes this a masterclass in engineering. In 2026, these machines utilize grade control technology. This means the operator in the cab is not just eyeballing the depth of a trench. Instead, GPS sensors mounted on the machine communicate with a 3D model of the job site. The hydraulics automatically adjust the bucket's position to ensure the trench is dug to the exact millimeter specified in the blueprints. This eliminates the need for manual surveying and drastically reduces the potential outcomes of human error. If Sarah's team is digging a foundation for a skyscraper, the excavator knows exactly where the bedrock is before the steel even touches the dirt. But the excavator is only half of the story. To move that earth, you need the articulated dump truck, or ADT. Unlike a standard dump truck that you might see on a highway, an ADT is designed for terrain that would swallow a normal vehicle whole. The defining feature of an ADT, like the Volvo A60H, is the oscillating hitch between the tractor and the trailer. This allows the front and back of the truck to rotate independently. If the front wheels hit a massive boulder and tilt 10 degrees to the left, the rear dump body can stay perfectly level. This ensures that all 6 wheels maintain contact with the ground at all times, providing maximum traction in the thick red clay of Georgia or the loose sand of Arizona. In 2026, these trucks are often equipped with autonomous hauling systems, allowing them to follow a predetermined path from the excavator to the spoil pile without a driver in the cab, a trend that has significantly increased efficiency in large-scale earth-moving projects. Then we have the bulldozer, the ultimate symbol of American construction power. A machine like the Cat D11 is a 230,000-pound beast designed for one thing: pushing. The tracks on a D11 are not just there for traction. They are designed to distribute that immense weight so the machine doesn't sink. The ground pressure of a bulldozer is surprisingly low, often less than that of a human foot, because the surface area of the tracks is so large. This allows a D11 to work on soft, unstable ground, while pushing a blade filled with 45 tons of rock. The mechanics of the blade are equally impressive. Modern dozers use power angle tilt blades that can be adjusted in 6 different directions with a single joystick, allowing the operator to crown a road or cut a precise drainage ditch in a single pass. However, owning these machines is a massive financial undertaking. This leads us into the high-stakes world of heavy equipment auctions. In 2026, companies like Ritchie Brothers and Iron Planet dominate the secondary market. Imagine a contractor named Mark in Pennsylvania who needs to expand his fleet, but cannot wait 18 months for a new machine from the factory due to ongoing supply chain shifts. He turns to the auction block. These are not like car auctions. They are global events where millions of dollars change hands in seconds. A 5-year-old excavator with 6,000 hours on the engine might still command a price of $350,000. The valuation of these heavy vehicles is a science in itself. Buyers like Mark look for specific data points. The most critical is the undercarriage remaining percentage. The undercarriage, including the tracks, rollers, idlers, and sprockets, represents about 50% of the maintenance cost over the life of a tracked machine. If the tracks are worn down to 20%, Mark knows he is looking at a $40,000 repair bill the moment the machine arrives at his shop. He also checks the fluid analysis reports. In 2026, every major heavy vehicle undergoes regular blood tests, where the oil is analyzed for microscopic metal shavings. If the hydraulic oil shows high levels of copper, it's a sign that the expensive piston pump is about to fail. Historical trends show that machines with a documented history of clean fluid samples sell for a 15% premium. The environmental regulations of 2026 have also fundamentally changed the heavy vehicle landscape. All modern diesel engines in this class must meet Tier 4 final or the emerging Tier 5 emission standards. This involves the use of diesel exhaust fluid and complex selective catalytic reduction systems to turn nitrogen oxide into harmless water vapor and nitrogen. For an owner like Mark, this means he has to manage not just fuel, but a whole secondary system of chemical treatment. A failure in the emission system can put the entire 500,000-pound machine into limp mode, rendering it useless on a high-priority job site. This has led to a surge in the value of older pre-emission machines, though many federal contracts now require the use of newer, cleaner technology as a prerequisite for bidding. As we move deeper into the dirt, we start to see the specialized variants that many people forget exist. There are the forestry harvesters that can cut, delimb, and stack a 60-foot pine tree in under 30 seconds. There are the massive pipe layers that use offset counterweights to keep from tipping over, as they lower miles of steel natural gas lines into the earth. Each of these is a heavy vehicle designed for a niche that is essential to the American way of life. They are the silent workers that ensure your water flows, your lights stay on, and your roads are built. But what happens when the job site is not a suburban housing development, but a massive open-pit mine in Nevada or the Iron Ranges of Minnesota? The machines we have discussed so far would look like toys compared to what is coming next. We are moving from the world of construction into the world of ultra-class mining. We are talking about trucks so large that they cannot be driven on any road in the world. They arrive at the site in dozens of shipping containers and take a team of engineers 6 weeks to assemble. In the next part, we are going to step into the cab of a vehicle that stands 3 stories tall and uses tires that cost $50,000 each. We will explore how these giants move 400 tons of rock in a single trip and why their engines are actually massive electric generators. The scale of the heavy vehicle world is about to become almost incomprehensible. To enter the world of ultra-class mining is to step into a realm where the laws of standard automotive physics are pushed to their absolute breaking point. In 2026, the demand for rare earth minerals and copper has reached a fever pitch to support the global shift toward electrification. And at the heart of this extraction effort is the ultra-class haul truck. Consider a mining engineer named Jack, working at a massive open-pit copper mine in eastern Nevada. When Jack looks out the window of his office in 2026, he isn't looking at trucks. He is looking at moving buildings. These machines, like the Caterpillar 797F or the Komatsu 980 x 10 to the power of -5, represent the apex of heavy vehicle engineering. The scale of an ultra-class truck is difficult to visualize until you are standing next to one. The Caterpillar 797F stands over 23 feet tall when the dump body is down. When it raises that body to dump 400 tons of rock, it reaches a height of over 50 feet, which is equivalent to a 5-story building. But the most shocking aspect of these vehicles isn't just their size. It is how they move. Unlike a standard semi-truck that uses a traditional mechanical transmission, Many ultra-class giants in 2026 utilize an AC electric drive system. In this setup, the massive 20-cylinder diesel engine, producing upwards of 4,000 horsepower, does not directly turn the wheels. Instead, it acts as a massive onboard power plant. This engine drives an alternator that converts mechanical energy into high-voltage electricity. That electricity is then sent through massive cables to electric induction motors located inside the rear wheel hubs. This is essentially a giant diesel-electric locomotive on rubber tires. The reasoning behind this design is efficiency and control. Mechanical transmissions for 4,000 horsepower would be prohibitively heavy and prone to failure under the extreme torque required to move 1.3 million pounds of total gross vehicle weight. With an electric drive, the truck has maximum torque from 0 miles per hour, allowing it to crawl out of a deep mine pit with a full load without shifting gears. The potential outcomes of using these electric drive systems are seen in the maintenance logs. Historical trends in the mining industry show that electric drive trucks often have higher availability rates than their mechanical counterparts because they have fewer moving parts in the drivetrain. In 2026, Jack's fleet in Nevada is almost entirely autonomous. These trucks use a combination of LiDAR, radar, and high-precision GPS to navigate the mine 24 hours a day, 7 days a week, only stopping for fuel and scheduled maintenance. This removes the human element from the most dangerous part of the operation, as a 400-ton truck has blind spots that could swallow an entire fleet of pickup trucks. Now, let us talk about the tires, which are perhaps the most expensive and specialized component of any heavy vehicle. A single tire for an ultra-class truck, like a 59/80 R63, stands over 13 feet tall and weighs nearly 12,000 pounds. In 2026, the cost of one of these tires can exceed $50,000. They are not filled with air. They are filled with nitrogen to prevent internal combustion in the event of extreme heat buildup. The manufacturing process for these tires is so complex that there are only a handful of factories in the world, owned by giants like Michelin and Bridgestone, capable of producing them. The maintenance of these tires is a masterclass in precision. Jack's team uses real-time pressure and temperature monitoring systems that send data every second to a central command hub. If a tire on truck 42 begins to overheat due to a slight misalignment or an overloaded bucket, the system automatically slows the truck down. This is critical because a tire blowout on a vehicle of this size is not just a flat, it is an explosion. The amount of stored energy in a tire pressurized to 100 psi at this volume is equivalent to several sticks of dynamite. Case studies in mining safety emphasize the 300-foot exclusion zone required when a tire is suspected of having a heat-related structural failure. The logistics of getting these vehicles to a mine site is a feat that many people never consider. You cannot drive a Caterpillar 797F down the I-15. These trucks are shipped in pieces. The frame, the engine, the dump body, and the tires arrive on dozens of specialized flatbed trailers, often requiring police escorts and temporary road closures. Once at the mine, a team of specialized technicians spends 4 to 6 weeks assembling the truck in a dedicated bay. It is a literal $5 million Lego set. The welding on the dump body alone takes hundreds of man-hours, as it must be reinforced with wear-resistant steel plates to survive the impact of 50 tons of jagged rock being dropped from a cable shovel. The fuel consumption of these machines is equally staggering. In a heavy work cycle, an ultra-class truck can burn through 60 to 70 gallons of diesel fuel per hour. In 2026, mining companies are looking at historical trends and realizing that fuel is their largest operating expense. This has led to the implementation of trolley assist systems. In some of the deepest mines in the United States, you will see massive overhead electric wires, similar to those used by city buses or trains. When the truck starts its climb out of the pit, it connects to these wires via a pantograph on the cab. The truck then switches from diesel power to direct electric power from the grid, allowing it to climb the grade at twice the speed while saving thousands of gallons of fuel per day. But it isn't just about moving the rock. It's about what loads the rock. To keep a fleet of these trucks moving, you need a shovel like the P&H 4100 XPC. This is a cable shovel that stands 60 feet tall and can scoop up 120 tons of earth in a single pass. It takes only 4 passes to fill a 400-ton truck. The coordination between the shovel and the truck is a choreographed dance. In 2026, the shovel operator sees a digital display showing the exact weight in the truck's bed in real time. Overloading a truck by even 10% can lead to premature frame cracking and tire failure, while underloading it by 10% results in millions of dollars in lost productivity over a year. As we look at these mining giants, It is clear that they represent the absolute limit of what we can achieve with current materials science and engineering. They are the primary engines of the global economy, providing the raw materials for everything from the smartphone in your pocket to the steel in your skyscraper. However, as massive as these mining trucks are, they operate in a controlled private environment. They never have to deal with traffic, pedestrians, or the unpredictable nature of the American highway. There is another class of heavy vehicle that is just as specialized, nearly as large, and far more common across the American heartland. These are the machines that ensure the world is fed. In the next part of this deep dive, we are moving from the mines of Nevada to the cornfields of Iowa and the wheat belts of Kansas. We are going to explore the high-tech world of agricultural heavy vehicles, where a single machine can harvest 100 acres a day with sub-inch accuracy. We will break down the mechanics of the modern combine harvester, a vehicle so complex it is essentially a factory on wheels, and we will look at how autonomous swarms are beginning to replace the lone farmer in the cab. The scale of American agriculture is about to be revealed in a way you have never seen before. Imagine a farmer named Miller standing at the edge of a 3,000-acre cornfield in central Iowa. It is late September 2026, and the window for a perfect harvest is shrinking. In decades past, Miller would have needed a dozen laborers and weeks of backbreaking work to clear this land. Today, he climbs into the pressurized, climate-controlled cab of a John Deere X9 1100, a machine that is less a tractor and more a mobile industrial processing plant. This is a Class 11 combine harvester, the largest category of agricultural heavy vehicle currently in operation in the United States. To understand why this machine is the literal lifeblood of the American food supply, we have to look at the sheer complexity of what happens inside that green and yellow steel skin as it moves at 4 miles per hour through a sea of golden stalks. The process begins at the header. For corn, Miller uses a 16-row folding corn head. As the combine moves forward, the header performs several high-speed mechanical actions simultaneously. It gathers the stalks, pulls them down with specialized snapping rolls, and removes the ear of corn from the plant. In 2026, these headers are equipped with individual row unit sensors that detect the thickness of the stalks and adjust the deck plates in real time to ensure no ears are dropped. Historical trends show that even a 1% loss of grain at the header can result in thousands of dollars of lost revenue over a large farm. This is why the engineering of the header is a masterclass in precision. Once the ear is separated, it is moved by a massive crossauger into the feeder house, a high-speed conveyor that shoots the crop into the heart of the machine. Inside the combine, we encounter the threshing and separation system. This is where the machine truly earns its name, as it combines the tasks of reaping, threshing, and winnowing. The X9 uses a dual rotor system. Imagine two massive, spinning steel cylinders equipped with brass bars. These rotors spin at high speeds, rubbing the ears of corn against concave grates. This centrifugal force and friction separate the individual kernels from the cob. The cob and the leftover plant material, known as MOG or material other than grain, are pushed out the back of the rotors. Meanwhile, the precious kernels fall through the grates into the cleaning shoe. The cleaning shoe is a masterpiece of fluid dynamics and vibration. It consists of a series of sieves that shake violently while a massive fan blows a controlled stream of air through them. This is the winnowing process. The air is calibrated to be strong enough to blow away the light dust and chaff, but not so strong that it lifts the heavy corn kernels. In 2026, Miller's combine uses AI-driven cameras inside the cleaning shoe to monitor the grain quality in real time. If the system detects too much broken grain or too much trash in the tank, it automatically adjusts the fan speed and sieve openings. This level of automation ensures that the grain reaching the storage tank is over 99% pure, a historical trend of efficiency that was unimaginable 20 years ago. While Miller is harvesting, he is not alone. To keep a Class 11 combine moving, you need a perfectly synchronized logistical dance. This brings us to the grain cart, typically pulled by a high-horsepower row crop tractor like a John Deere 9R. Imagine if Miller had to stop every time his 420-bushel grain tank was full. He would lose 30% of his daily productivity. Instead, a second operator, or in some 2026 case studies an autonomous tractor, pulls the grain cart alongside the combine while it is still harvesting. Miller extends a 20-foot unloading auger, and with the push of a button, he dumps 420 bushels of corn into the moving cart in less than 2 minutes. The volume of grain being moved is staggering. An X9 1100 can harvest up to 7,200 bushels of high-yield corn per hour. That is enough to fill 2.5 full-size semi-trucks every 60 minutes. But the heavy vehicle involvement doesn't end in the field. This grain must be transported to a local elevator or a massive grain terminal. This is where the Class 8 semi-trucks we discussed in earlier parts return to the story, but with a specialized twist. Agricultural trucking involves navigating soft field roads and high-traffic rural highways. These trucks often use hopper-bottom trailers, which feature sloped internal walls and manual or electric gates at the bottom to quickly unload grain into underground pits. The weight of these vehicles is a constant concern for rural infrastructure. A fully loaded grain truck can weigh 80,000 pounds or more, and in 2026, many states have implemented weight limit exemptions during harvest season to allow farmers to move more crop faster, provided they follow strict safety and axle distribution guidelines. The financial scale of these agricultural heavy vehicles is just as massive as their mechanical footprint. A new Class 11 combined with both a corn head and a small grain header can easily exceed $1.2 million in 2026. This is a significant investment for a family farm like Miller's. To justify this cost, these machines are designed to be as productive as possible. This has led to the rise of autonomous swarm technology. Case studies from large-scale operations in the Dakotas and Nebraska are now showing the potential outcomes of using one human-operated combine as a lead vehicle, with 2 or 3 fully autonomous combines following its path. This swarm approach allows a single crew to harvest thousands of acres in a fraction of the time, reducing the risk of crop loss due to late-season snow or rain. Another critical aspect of these machines is their impact on the soil. A 100,000-pound machine moving across a field can cause severe soil compaction, which crushes the pore spaces in the earth and prevents water and air from reaching the roots of next year's crop. To solve this, heavy agricultural vehicles in 2026 are increasingly moving away from tires and toward massive rubber track systems. These tracks distribute the weight over a much larger surface area. While a tire might exert 30 pounds per square inch of pressure on the soil, a track system can reduce that to as little as 10 or 12 psi, which is roughly equivalent to the footprint of a human. This engineering choice is a direct response to historical trends showing that compacted soil can reduce future yields by up to 15%. The sheer scale of American agriculture is built on these roaring high-tech titans. Without the Class 11 combine, the grain cart, and the specialized Class 8 transport trucks, the global food market would collapse. These are the machines that turn the vast plains of the Midwest into the breadbasket of the world. Every component, from the snapping rolls on the header to the AI sensors in the cleaning shoe, is optimized for one goal: maximum calorie extraction with minimum waste. But as specialized and powerful as these agricultural machines are, they are confined to the dirt and the rural backroads. There is another category of heavy vehicle that must be ready to operate anywhere, at any time, under the most extreme conditions imaginable. These are the vehicles that the public hopes they never have to see in their driveway, yet they are the ones we rely on during our darkest hours. In the next part of this masterclass, we are leaving the fields of Iowa and heading into the world of emergency and disaster response. We are going to tear down the mechanics of the massive ARFF vehicles found at airports, the heavy-duty tiller fire trucks that navigate the tightest streets of San Francisco, and the specialized amphibious vehicles used by the National Guard during flood rescues. The stakes are about to get much higher as we look at the heavy vehicles designed to save lives. Imagine Alex, an emergency response specialist at a major international hub, like Denver International Airport in 2026. While most travelers are focused on their boarding passes, Alex is focused on a machine that looks like it belongs in a science fiction film, the Oshkosh Striker 8x8. This is not a standard fire engine. It is an aircraft rescue and firefighting vehicle, or ARFF. In the world of heavy vehicles, the ARFF represents the peak of rapid response engineering. If a wide-body jet encounters a mechanical failure on the runway, Alex has exactly 90 seconds to reach the scene. To achieve this, the Striker 8x8 utilizes dual rear engines producing 1,540 horsepower, allowing this 100,000-pound beast to accelerate from 0 to 50 miles per hour in under 25 seconds. This is a historical trend in airport safety where the sheer mass of the vehicle must be overcome by massive power to ensure survival in high-stakes scenarios. The primary weapon of the ARFF is its water and foam capacity. Alex's vehicle carries 4,500 gallons of water and 630 gallons of fire-suppressing foam. The roof-mounted turret can throw this mixture over 300 feet, allowing the vehicle to fight a fire from a safe distance while moving at speed. But the real engineering marvel is the high-reach extendable turret, often called the snozzle. This is a piercing nozzle that can punch through the high-strength aluminum or composite fuselage of a burning aircraft to deliver water or foam directly into the cabin or cargo hold. This technology allows firefighters to cool the interior of a plane before rescue teams even enter, which significantly improves potential outcomes for passengers. In 2026, these vehicles are also equipped with thermal imaging cameras that can see through thick smoke and darkness, highlighting heat signatures from hundreds of yards away to locate the source of a fire instantly. Now imagine if you were tasked with driving a 60-foot-long vehicle through the tight, hilly streets of San Francisco or the narrow alleys of Boston. This is the daily reality for operators of the tractor-drawn aerial, commonly known as a tiller truck. The tiller is one of the most distinctive heavy vehicles in the American Fire Service because it requires two drivers. There is the primary driver in the tractor cab at the front, and then there is the tillerman, who sits in a small, elevated cab at the very rear of the trailer. This rear driver is responsible for steering the back wheels independently of the front. The physics of a tiller truck are fascinating. Because the rear wheels steer, the trailer can follow the tractor's path with incredible precision, or it can be steered in the opposite direction to allow the 60-foot truck to make a turn that would be impossible for a standard ladder truck. In 2026, this mechanical articulation is a masterclass in urban logistics. The rear driver must have an intuitive sense of the truck's pivot point, which is the fifth wheel connection between the tractor and the ladder trailer. Case studies from metropolitan fire departments show that tillers are often the only way to get a 100-foot aerial ladder into a tight residential block. Without this heavy vehicle, high-rise rescues in historic American cities would be nearly impossible. When we move from the city to the forest, the nature of heavy vehicles changes again. The western United States is the primary theater for wildfire response, and the heavy hitters here are the tactical water tenders and the fire dozers. A tactical water tender is a heavy-duty 6x6 truck designed to carry up to 4,000 gallons of water over unpaved, mountainous terrain. These are not built for speed like the ARFF. They are built for low-end torque and durability. They often feature high-clearance suspensions and central tire inflation systems, which allow the driver to lower the tire pressure from the cab to increase the tire's footprint on soft soil or sand. This ensures that the 60,000-pound vehicle doesn't get stuck while delivering critical water to fire crews on the front lines. Supporting these tenders are the fire dozers, typically Caterpillar D6 or D7 models equipped with specialized protective cages and high heat-resistant glass. The role of a fire dozer is not to put out the fire, but to starve it. These machines are used to create fire breaks, wide paths cleared of all vegetation and fuel. Imagine a dozer operator in 2026 pushing through thick brush and timber in the Sierra Nevada, working through the night to clear a mile-long line before the wind shifts. The blade of a fire dozer is reinforced to handle the impact of falling trees and boulders, and the machine's low center of gravity allows it to operate on slopes that would flip a standard vehicle. This is a high-risk environment where the machine is the only thing standing between a community and a fast-moving blaze. Disaster response also requires heavy vehicles that can ignore the standard rules of the road, specifically, where the road ends and the water begins. During hurricane season or extreme flooding events in 2026, the National Guard relies on the family of medium tactical vehicles, or FMTV. The M1083 MTV is a 5-ton, 6x6 truck designed for the U.S. Army, but its role in civilian disaster relief is unparalleled. These trucks feature a 50-inch water fording capability. This means they can drive through 4 feet of moving floodwater to reach stranded residents or deliver supplies. The engineering behind this includes elevated air intakes for the engine and sealed electrical systems that prevent the vehicle from shorting out when submerged. Step by step, the deployment of an MTV in a flood zone is a precision operation. The driver first engages the deep water fording mode, which pressurizes the drivetrain components to keep water from seeping into the axles and transmission. As the vehicle enters the water, the massive 46-inch tires provide enough displacement to help the truck feel light. Yet the heavy steel frame and powertrain ensure it remains grounded against the current. Case studies from recent flood events in the Gulf Coast demonstrate that these heavy vehicles are often the only way to conduct mass evacuations when standard rescue boats are hindered by debris or shallow water. In the realm of heavy rescue, we must also consider the technical rescue squad trucks. These are essentially moving toolboxes the size of a city bus. They carry thousands of pounds of hydraulic extrication equipment, heavy-duty shoring for collapsed buildings, and high-pressure lifting bags capable of raising a 50,000-pound concrete slab. In 2026, these vehicles are the nerve centers of major accident scenes. They are equipped with onboard generators that can power high-intensity light towers for days, turning a midnight highway crash site into a daylight-bright workspace. The weight distribution on these vehicles is critical. Every compartment is meticulously organized so that the heaviest tools are stored low to maintain a stable center of gravity during high-speed emergency responses. As we analyze these life-saving machines, it is clear that their design is dictated by the specific extremes they must face. Whether it is the heat of a jet fuel fire, the tight corners of an urban center, or the rising waters of a flood, these heavy vehicles are the ultimate tools of the American emergency response system. They are the physical manifestation of our commitment to safety and resilience. Every time you see one of these giants on the move, you are seeing $1 million investment in human life. But there is another side to the heavy vehicle world, one that is less about saving lives and more about the raw power required to defend a nation. The engineering that goes into moving a 70-ton tank across the desert or transporting a nuclear-capable missile is on a level of complexity that dwarfs even the most advanced fire truck. In the next part of this deep dive, we are entering the world of military heavy movers. We are going to look at the HET, the heavy equipment transporter, and the massive logistics chain that allows the US military to move an entire armored division across the globe in a matter of days. We will explore the mechanics of tank hauling and the specialized trailers that turn a truck into a mobile platform for the most powerful weapons on Earth. The scale is about to shift from domestic service to global power projection. The logistical backbone of the United States military does not rest on the wings of fighter jets or the hulls of destroyers alone. It rests on the massive multi-axle tires of the Heavy Equipment Transporter, or HET. To understand the scale of military heavy vehicles in 2026, we have to look at the primary problem the Army faces: the M1A2 SEPV-3 Abrams main battle tank. This vehicle is a 73-ton masterpiece of armor and firepower, but it is also a mechanical nightmare to move over long distances. While it can travel at speeds of up to 45 miles per hour, doing so on a paved highway would shred the asphalt and consume an astronomical amount of fuel while wearing down the expensive rubber track pads. This is where the Oshkosh M1070A1 enters the frame. Imagine a logistics officer named Captain Rodriguez at the port of Savannah in 2026. Her mission is to move an entire armored company from the docks to a training range hundreds of miles inland within a 48-hour window. This is not a simple trucking job. It is a high-stakes engineering operation. The M1070A1 HET is an 8x8 tractor designed specifically to haul loads that would crush a standard commercial semi-truck. Under the hood sits a 18.1-liter Caterpillar C18 diesel engine, churning out 700 horsepower and an incredible 1,900 pound-feet of torque. This engine is mated to an Allison 4800 SP 7-speed automatic transmission, which is critical for maintaining momentum when a 230,000-pound gross combined weight rig hits a 6% grade. The tractor is only half of the equation. The real star of the heavy lift show is the M1000 Heavy Equipment Transporter semi-trailer. To prevent the 73-ton tank from falling through the road surface, the M1000 utilizes 40 tires spread across 5 axle lines. Each axle line features 2 half-axles that can pivot, allowing the trailer to navigate tight turns that a standard fixed-axle trailer could never manage. The suspension is entirely hydraulic, allowing the trailer bed to be raised or lowered to clear obstacles, or to create a level loading platform on uneven terrain. Historical trends in military logistics show that the move toward hydraulic suspension has drastically reduced the time required to load and unload disabled vehicles, as the trailer can literally kneel to the ground. The step-by-step process of loading an Abrams onto a HET is a masterclass in precision. Rodriguez watches as the tank commander carefully guides the massive machine up the rear ramps. If the tank is operational, it drives up under its own power, but if it is a recovery mission for a disabled unit, the HET's dual 55,000-pound capacity winches come into play. These winches, mounted behind the cab, use steel cables thick enough to pull a house off its foundation. They work in tandem to slowly drag the dead weight of the tank onto the trailer deck. Once positioned, the tank is secured with heavy-duty chains capable of withstanding the G-forces of a sudden stop or a high-speed maneuver. In 2026, these chains are often replaced by synthetic high-tension tie-downs that provide the same strength with a fraction of the weight. A case study in material science improving logistical efficiency. But what happens when the road ends? This is where the Central Tire Inflation System, or CTIS, becomes a life-saving feature. From the comfort of the air-conditioned cab, the driver can adjust the air pressure in all 8 tractor tires and all 40 trailer tires simultaneously. If the rig hits soft sand or deep mud, the driver selects the appropriate setting, and the system bleeds air out to increase the tire's footprint, effectively turning the tires into tracks. Once they return to the pavement, the system pumps the tires back up to highway pressure to ensure stability and fuel efficiency. This ability to adapt to the environment is why the HET remains the king of the off-road heavy-haul world. In 2026, we are also seeing the integration of autonomous convoy technology, often referred to as leader-follower systems. In a high-risk environment, the lead HET is driven by a human, but the following 3 or 4 trucks are entirely unmanned. They use a suite of LiDAR and short-range radio links to mirror the exact path, speed, and braking of the lead vehicle. Potential outcomes of this technology include a significant reduction in human casualties during transport missions in unstable regions, as fewer soldiers are exposed to the dangers of the road. This transition from manual to semi-autonomous heavy hauling is one of the most significant shifts in military vehicle history. The complexity of these machines extends to their maintenance. A single HET rig in 2026 represents an investment of over $1 million. To protect this investment, the vehicles are equipped with health and usage monitoring systems that track everything from the temperature of the wheel hubs to the quality of the transmission fluid. If a sensor detects an anomaly, the data is beamed via satellite to a maintenance hub, allowing mechanics to have the necessary parts ready before the truck even pulls into the motor pool. This predictive maintenance is a historical trend that has moved the military away from the old break-fix model toward a high-availability fleet. Beyond the tank hauler, we have the specialized heavy movers of the Air Force. These include the massive loaders used to move pallets of munitions and supplies into the yawning maws of C-5 Galaxy and C-17 Globemaster transport planes. The Tonner 60K loader is a heavy vehicle that can lift 60,000 pounds of cargo to a height of 18 feet, and then drive it directly onto an aircraft. The deck of the Tonner can pitch, roll, and yaw to align perfectly with the plane's cargo floor, even if the plane is parked on a slight slope. This level of hydraulic precision ensures that millions of dollars of sensitive equipment can be loaded without a single bump. As we look at these military giants, it becomes clear that their primary purpose is the management of extreme weight in extreme environments. They are the enablers of global power, ensuring that the heavy armor and supplies needed to defend a nation can be delivered anywhere on the planet in a matter of days. The engineering required to make a 100,000-pound truck move a 140,000-pound tank through a desert is a pinnacle of human achievement. However, the military isn't the only sector that needs to move impossibly heavy objects. There is a civilian world of heavy hauling that deals with even larger loads, objects so big they require their own zip code. We are talking about the overdimensional loads that move under the cover of night, escorted by police and utility crews. These are the components of the next generation of American power and exploration. In the next part of this deep dive, we are going to explore the world of super heavy civilian transport. We will look at the vehicles that move 200-foot wind turbine blades and the massive rocket boosters destined for the launch pads of Florida and Texas. We will break down the logistics of the multi-state permit process and the specialized steerable trailers that allow a load longer than a city block to navigate a suburban roundabout. The scale is about to leave the ground and head for the stars. To truly understand the outer limits of American heavy hauling in 2026, we have to look at the transition from standard freight to overdimensional and super heavy loads. This is the world of Marcus, a logistics lead for a specialized transport firm based out of Houston, Texas. In 2026, Marcus is not just moving boxes, he is moving pieces of the future. His current project involves the transport of a 270-foot wind turbine blade from a manufacturing facility in Colorado to a new wind farm in the Texas Panhandle. A load of this length is physically impossible for a standard trailer to manage. To move it, Marcus utilizes a specialized steerable stretch trailer. The engineering of a stretch trailer is a study in structural integrity and flexibility. These trailers can extend their length from a standard 53 feet to well over 200 feet, using a telescoping spine made of high-tensile steel. However, the length creates a massive problem for navigation. Imagine Marcus trying to turn a 300-foot-long vehicle through a standard intersection. The rear of the trailer would swing hundreds of feet off the road, obliterating everything in its path. To solve this, the rear axle assembly, known as the dolly, is independently steerable. In 2026, this is managed by a rear steer operator, a second person sitting in a pilot car behind the trailer with a remote control that allows them to steer the trailer's wheels separately from the truck steering. This creates a dual steering system that allows the load to crab walk around corners or follow a precise path through a roundabout. The physics of wind energy logistics is a high-stakes game. A single blade for a 2026-era offshore or high-altitude turbine can weigh over 20 tons and cost hundreds of thousands of dollars. Historical trends in the energy sector show that as turbines get larger to capture more wind at higher altitudes, the transport challenges grow exponentially. Marcus must coordinate with utility companies weeks in advance. When a load is this tall or wide, it may require bucket trucks to precede the convoy, physically lifting power lines or temporarily removing traffic signals to allow the load to pass. This is not just driving. It is a coordinated civil engineering project in motion. But wind blades are light compared to the heavy hitters of the aerospace industry. In 2026, the American space economy has moved into high gear, requiring the transport of massive rocket boosters and pressure vessels from manufacturing hubs to launch sites like Cape Canaveral or Boca Chica. For these loads, the weight is so extreme that traditional axles would simply crush the road surface. Here, Marcus employs self-propelled modular transporters, or SPMTs. An SPMT is a platform on wheels that looks like a flat, steel deck, but underneath, it is a mechanical marvel. Each individual wheel can rotate 360 degrees independently, and the entire platform can be raised or lowered by over 20 inches using an integrated hydraulic suspension. The step-by-step operation of an SPMT is fascinating. Multiple modules can be linked together side by side or end-to-end to create a platform the size of a football field. In 2026, these units are controlled by a single operator with a handheld console. The computer system ensures that the weight is distributed perfectly across every tire. If the ground is uneven, the hydraulic suspension automatically adjusts to keep the multi-million-dollar rocket booster perfectly level. Case studies from NASA and private aerospace firms show that the use of SPMTs has reduced the potential outcomes of structural stress on sensitive hardware during transport, as the platform eliminates the vibrations and jolts associated with traditional trailers. The logistics of these superloads require a massive amount of data and permitting. In 2026, Marcus uses swept path analysis software to run a digital simulation of the entire route before the truck even leaves the yard. This software uses satellite imagery and LiDAR road scans to identify every potential pinch point. If a bridge is too weak or an underpass is 2 inches too low, the route must be redesigned. Historical trends in the Department of Transportation show a move toward national overdimensional permits to streamline the process, but Marcus still has to navigate the specific laws of every state he crosses. For example, some states require a police escort for anything over 16 feet wide, while others mandate that super heavy loads only move during daylight hours or on weekends to minimize the impact on public traffic. We also have to consider the massive transformers and generators that keep the American grid alive. A single baseload transformer can weigh over 800,000 pounds. Moving this requires a dual-lane trailer or a schnabel trailer. A schnabel trailer is a specialized vehicle where the load itself becomes a structural part of the trailer. The transformer is suspended between two massive hydraulic arms that grip it at either end. This allows the load to be carried just inches above the ground, which is critical for clearing low bridges. In 2026, the demand for these massive components has surged as the United States upgrades its aging electrical infrastructure. The economic impact of these heavy vehicles is immense. Without the ability to move these overdimensional loads, the transition to renewable energy would stop, and the aerospace industry would be grounded. Case studies in infrastructure development show that the efficiency of heavy-haul logistics is a primary driver of the total cost of energy projects. If Marcus can find a way to move 3 turbine blades in a single convoy instead of one, the potential outcomes include lower electricity prices for millions of Americans. However, as the machines get larger and the loads get heavier, the strain on the human element increases. Operating a vehicle that is 200 feet long or weighs 1 million pounds is a job for only the most elite drivers and coordinators. These operators are part engineers, part pilots, and part diplomats. They have to manage local law enforcement, utility crews, and the impatient public while ensuring that a single wrong move doesn't cause a multi-million-dollar disaster or an infrastructure collapse. The specialized training for these roles is rigorous. In 2026, many heavy-haul firms use high-fidelity VR simulations to train their drivers on how to handle a jackknife scenario or a brake failure on a steep grade with a superload. The mechanical systems are also becoming more autonomous, with sensors that can detect a microscopic crack in a trailer's frame before it leads to a catastrophic failure. This fusion of massive iron and digital precision is the current state of the art in American heavy hauling. As we look at these giants moving through the night, it is clear that they represent the absolute peak of what rubber and steel can do on public roads. They are the vehicles that make the impossible possible, moving the building blocks of our civilization one slow, careful mile at a time. But who are the people behind the wheel? What does it take to get the specialized licenses required to command these beasts? And what are the dangers that come with a life spent on the edge of mechanical limits? In the next part of this deep dive masterclass, we are going to focus on the human factor. We will break down the specialized CDLA endorsements, the high-stakes world of heavy vehicle safety inspections, and the grueling reality of life as an elite heavy haul operator. We are going to look at the stories of the men and women who keep the giants moving, even when the road ahead seems impassable. The scale of the training is about to match the scale of the machines. To command a machine that weighs as much as a small apartment building, you cannot simply be a driver. You must be a technician, a safety officer, and a high-stakes navigator all at once. In 2026, the path to becoming an elite heavy haul operator is more rigorous than it has ever been in the history of American logistics. Consider Sarah, a 35-year-old operator based out of Pennsylvania who specializes in moving bridge girders. To get behind the wheel of her custom-built Peterbilt 389, Sarah didn't just pass a driving test. She underwent a multi-year progression of certifications and high-fidelity simulations that reflect the historical trends of increasing regulation in the transportation sector. The foundation of this career is the Class A Commercial Driver's License, or CDLA. But for heavy vehicles, the basic license is just the entry ticket. In 2026, the Federal Motor Carrier Safety Administration has expanded the entry-level driver training requirements to include mandatory modules on advanced vehicle dynamics and electronic logging systems. Sarah's license is a tapestry of endorsements. She holds the N endorsement for tankers, which required her to master the fluid surge physics we discussed earlier. She has the H endorsement for hazardous materials, requiring a high-level background check and a deep understanding of chemical compatibility. Most importantly for her current role, she holds the T endorsement for doubles and triples, and she has completed specialized, non-standard certifications for over-dimensional loads. Step by step, the training for a heavy haul professional involves mastering the science of securement. This is where many newcomers fail. In 2026, Sarah doesn't just throw a chain over a piece of equipment and hope for the best. She uses a digital load calculator that factors in the weight of the cargo, the friction coefficient of the trailer deck, and the aggregate working load limit of her tie-downs. If she is hauling a 120,000-pound excavator, federal law requires that her tie-downs have a combined strength of at least half the weight of the load. However, in the professional world of heavy hauling, the potential outcomes of a load shift are so catastrophic that Sarah over-engineers her securement by 200%. She uses grade 120 square-link chains, which offer a higher strength-to-weight ratio than the standard grade 70 chains used in general freight. Imagine the mental load as Sarah begins her pre-trip inspection, a process colloquially known as walking the iron. In 2026, this is a 45-minute ritual. She starts at the front of the tractor, checking the steer axle tires for any signs of irregular, where that could indicate an alignment issue. She inspects the leaf springs for cracks and ensures the shock absorbers are not leaking. Then comes the air system. Sarah performs a formal air brake test. She pumps the brakes down to 60 psi to ensure the low air warning light and buzzer activate, then continues to pump until the protection valves pop out, usually between 20 and 40 psi. This ensures that if she loses an air line on a mountain pass, the fail-safe spring brakes will automatically lock the wheels. The most stressful part of Sarah's day isn't the driving. It's the interaction with the Commercial Vehicle Safety Alliance, or CVSA. In 2026, roadside inspections have become high-tech affairs. When Sarah pulls into a weigh station in Ohio, her truck's onboard diagnostic system communicates via short-range radio with the DOT's computers. This is a Level 8 electronic inspection, which checks her hours of service logs, vehicle weight, and registration status without her even stopping. However, if she is selected for a Level 1 North American Standard inspection, a certified officer will spend an hour under her truck. They will measure the pushrod travel on every brake chamber to the fraction of an inch. If a single brake is out of adjustment by more than 2 inches, the vehicle is placed out of service. Historical trends show that these rigorous inspections have significantly reduced mechanical failure accidents, but for the driver, it means the margin for error is effectively zero. The life of a heavy haul operator in 2026 is also a study in human endurance and mental health. Sarah lives by the 14-hour rule. Once she starts her clock, she has 14 hours to complete her work, and only 11 of those can be spent driving. In 2026, the electronic logging devices, or ELDs, are integrated with the truck's engine and GPS. There is no more paper log manipulation. The truck is a snitch. This has led to a case study in the trade-off between safety and flexibility. While it prevents driver fatigue, it also creates a high-pressure environment where Sarah must find a safe place to park a 100-foot-long vehicle before her clock runs out. In 2026, smart parking apps and reserved spots at specialized truck stops have become essential tools for her survival on the road. Inside the cab, the environment has shifted from a greasing gears workspace to a high-tech flight deck. Sarah's seat is an active suspension unit that uses sensors to counteract the vibrations of the road, reducing the long-term risk of spinal compression and chronic back pain, a historical trend among veteran truckers. She has a multi-camera array that gives her a 360-degree bird's-eye view of her trailer, which is critical when navigating tight construction sites. In 2026, her truck is also equipped with a driver-facing camera and AI monitor. If the system detects Sarah's eyes closing or her head drooping for more than 2 seconds, it triggers a seat vibration and an audible alarm. While some drivers find this intrusive, the potential outcomes of preventing a highway-speed microsleep are undeniably positive. Consider the isolation of this life. Sarah might spend 3 weeks on the road, seeing the world through a windshield and communicating with her escort team via CB radio. The social structure of the heavy haul community is tight-knit. When she is moving a superload, she is the captain of a small fleet. She has a lead pilot car, a rear pilot car, and sometimes a police escort. The communication must be constant and precise. If the lead car sees a low-hanging branch or a pothole that could jolt a sensitive load, they relay that information instantly. This level of teamwork is what allows these giants to move through a crowded, distracted world with minimal incident. As we look at the human factor, it is clear that the machines are only as capable as the people who command them. Sarah represents a new generation of American heavy vehicle operators, tech-savvy, safety-obsessed, and highly specialized. She is the final link in the chain that connects the manufacturer to the job site. Without the skill to navigate a 150,000-pound load through a rainstorm at midnight, the advanced engineering of the truck and trailer would be useless. But the world Sarah operates in is on the verge of its most radical transformation since the invention of the internal combustion engine. The heavy vehicles of tomorrow are already being tested on the highways of the Southwest and the ports of the East Coast. We are moving toward a future where the roar of the diesel engine is replaced by the hum of electricity and the hiss of hydrogen, and where the driver in the cab might eventually become a remote supervisor sitting in an office miles away. In the final part of this deep dive masterclass, we are going to look into the future of American heavy vehicles. We will explore the revolutionary megawatt charging systems, the physics of hydrogen fuel cells for long-haul trucking, and the ultimate machines that are being designed to build our future colonies on other worlds. The journey is ending, but the future of the heavy vehicle is just beginning. As we stand at the edge of this technological horizon in late 2026, the definition of a heavy vehicle is being rewritten in real time. To understand where we are going, we have to look at the massive shift in how these machines are fueled and operated. Imagine a veteran driver named Leo pulling into a specialized terminal in North Platte, Nebraska. In years past, Leo would have headed straight for the high-flow diesel pumps. But today, in 2026, he is steering his tractor toward a megawatt charging system, or MCS. This is the new gold standard for heavy-duty electrification. An MCS is not like a standard car charger. It is a high-voltage industrial connection capable of delivering over 1 megawatt of power. To visualize this, consider that 1 megawatt is enough to power roughly 750 homes simultaneously. The cables are liquid-cooled to prevent them from melting under the extreme current, and the potential outcomes for the logistics industry are revolutionary. For a Class 8 truck like Leo's, this means adding 400 miles of range in less than 30 minutes, roughly the time it takes for a mandatory driver rest break. However, battery electric power is only one half of the future. For the truly long-haul routes, the 1,500-mile runs from Chicago to Seattle, the weight of the batteries required would begin to eat into the cargo capacity. This is where the United States is seeing a massive surge in hydrogen fuel cell technology. Case studies from ports in Long Beach and Savannah show that hydrogen-powered heavy vehicles can provide the range and refueling speed of diesel with zero tailpipe emissions. The only byproduct is pure water vapor. The mechanics involve high-pressure tanks storing hydrogen gas at 700 bar, which is then fed into a fuel cell stack where it combines with oxygen to create electricity. This electricity powers the drive motors, while a small buffer battery manages peak loads. Historical trends in the energy sector suggest that as the infrastructure for green hydrogen production scales up, these vehicles will become the primary choice for heavy haulers who cannot afford the downtime of charging. The operation of these future giants is also moving away from the traditional cabin steering wheel model. We are entering the era of the hub-to-hub autonomous transition. Imagine a fleet of trucks leaving a warehouse in Phoenix, Arizona, destined for a distribution center in Dallas, Texas. In 2026, these trucks are Level 4 autonomous, meaning they can navigate the I-10 corridor without any human intervention. There is no driver in the seat. Instead, there is a remote pilot like Leo, sitting in a centralized operations hub. Leo acts as a digital shepherd, monitoring a dozen trucks simultaneously. If a truck encounters a scenario its AI cannot resolve, such as a complex construction zone or a rare weather event, Leo takes control remotely via a low-latency 5G or satellite link. This shift is not just about efficiency. It is a response to the historical trend of driver shortages and the need for 24/7 logistics. Potential outcomes include a 30% reduction in transport costs and a significant increase in highway safety, as AI systems do not suffer from fatigue or distraction. But the most extreme frontier for American heavy vehicles isn't even on this planet. As part of the Artemis missions in 2026, the United States is developing the heavy vehicles that will build the first permanent lunar base. These are the lunar terrain vehicles and the autonomous regolith haulers. The engineering challenges here are unprecedented. These machines must operate in a vacuum, survive 2-week-long nights where temperatures drop to -250 degrees, and navigate a surface covered in moon dust that is as abrasive as crushed glass. Instead of rubber tires, which would brittle and shatter in the cold, these vehicles use non-pneumatic, spring mesh wheels made of titanium and nickel tin alloys. These wheels can deform over rocks and instantly return to their original shape, providing traction on the loose lunar soil. The power systems for these off-world heavy vehicles are also a masterclass in adaptation. They utilize vertical solar arrays to catch the low-angle sun at the lunar South Pole and regenerative fuel cells to store energy for the long lunar night. Case studies in space-based robotics show that the lessons learned from building these lunar bulldozers are already trickling back to Earth. For example, the dust sealing technology developed for the moon is being applied to heavy vehicles operating in the high desert mines of the American Southwest, where fine silica dust is a constant threat to mechanical longevity. Closer to home, the very infrastructure we drive on is being reimagined to accommodate these new giants. In 2026, we are seeing the first pilot programs for inductive charging lanes on major interstates. Imagine if a heavy vehicle didn't have to stop to charge or refuel at all. As the truck drives over specialized copper coils embedded beneath the asphalt, energy is transferred wirelessly to a receiver on the bottom of the chassis. This is the ultimate evolution of the heavy vehicle, a machine that is perpetually powered, allowing for non-stop transcontinental logistics. The step-by-step implementation of this technology involves a massive overhaul of the national grid, utilizing the highway right-of-ways for high-voltage DC transmission lines that feed both the charging lanes and nearby communities. As we conclude this deep-dive masterclass, it is clear that the heavy vehicle is no longer just a tool of transport. It is a mobile data center, a clean energy laboratory, and a pioneer of human expansion. From the Class 8 tractors that form the spine of our current economy to the autonomous lunar haulers that represent our future, these machines are the physical manifestation of our civilization's reach. The roar of the internal combustion engine may be fading, but the power of the heavy vehicle has never been greater. We have explored the mechanics of the fifth wheel, the physics of hydraulic excavators, the logistics of superloads, and the digital future of the autonomous convoy. You now understand the complexity, the danger, and the sheer brilliance required to keep the United States moving. The next time you are driving down the interstate and a massive rig pulls up alongside you, or you pass a construction site where yellow iron is reshaping the earth, you will see more than just a machine. You will see a century of engineering, a high-stakes financial investment, and a testament to the people who command these titans. The road ahead is longer and more complex than ever before, but the heavy vehicles of America are ready to meet it. The question is no longer whether we can move the world, but how much more of it we can move. If you think the machines we have discussed are impressive, Consider the massive seagoing vessels and heavy-lift aircraft that connect our road networks to the rest of the globe. This masterclass on the ground is just the first layer of the global logistics network. The integration of these trucks with the next generation of autonomous cargo ships and hypersonic freight planes is a story that is only just beginning to unfold. Would you like me to analyze the specific mechanics of the ultra-class sea freight haulers or the heavy-lift drone swarms that are now handling the last-mile delivery of industrial parts?